Hi, everyone. We are going to be waiting just a few minutes to let people kind of filter in, and then we will get started. All right, let's get started. Hello, welcome to another installment of the HEBI Robotics webinar series. My name is Colleen. I'll be moderating today's session. Please take note that the webinar today will be recorded, and the recording will be sent out to everyone attending as well as those that registered but could not attend, and will be available to view afterward. As we go through the presentation, all attendees will automatically be muted, but feel free to send us questions through both the chat function and the question feature located on the GoToWebinar sidebar. We'll do our best to answer them as they come in, but we do have some time set aside at the end to take questions. And with that, I'm going to hand it off to HEBI co-founder Dave Rollinson to get us started.
All right, hi. Thanks everyone for taking the time to join. Today we'll be introducing Tready and doing an overview of the platform and some other aspects of how we developed it. To start off with, we're going to show the Tready release video, which some of you guys may have already seen on YouTube. So we'll roll with that.
Meet HEBI Robotics' newest addition to our line of mobile bases, Tready. Right out of the box, Tready's ready to explore. Tready's built with the HEBI Robotics modular actuation platform and comes equipped with a computer, Wi-Fi, hot swappable batteries, and the option for tethered power. Important information is transferred from bot to being quickly and effortlessly. Tready's built with 8 actuators that make it possible for this robot to go where no robot has gone before. With individual control over its 4 flippers, Tready can climb the toughest obstacles. Tight crevices or gaps are no match for this bot. He maneuvers over uneven and challenging terrain. Stairs? Not a problem for Tready. He climbs up and down with ease. And even if he does make a misstep, he gets himself right back up. After finishing some land nav, Tready's ready for a dip. He's designed for an IP67 rating and is capable of maneuvering in water. Tready also handles large payloads, and like all HEBI Robotics kits, Tready is configurable. Add a HEBI arm, cameras, and LiDAR technology to create a customized Tready of your own. Thanks, Tready.
All right, so that was a fun overview of the platform. I understand not everyone may have been able to hear the audio to that. If not, that exact video is on YouTube. I'd recommend checking it out if you can. The narration's really great. There we go. Okay. Before we get going, I just want to give a little bit of background about myself and HEBI Robotics. I'm Dave Rollinson. I'm one of the co-founders of HEBI. I have a background in robotics from Carnegie Mellon University here in Pittsburgh. And HEBI Robotics is a spin-off from Carnegie Mellon that builds modular actuators and a development platform for robotics. We were founded in 2014. We've been selling products to researchers since 2016. And we have offices in Pittsburgh, Pennsylvania, where most of the team is, but we also have a European office in Salzburg, Austria. And one more little note is you might notice some clashing of branding between things like the video you just saw and the rest of the presentation here. We're undergoing a really exciting rebranding that we'll be unveiling over the next couple weeks. You'll see this change over on our website and kind of everything else that we have, but you're getting kind of a sneak peek of it here. So as an overview, what you can expect for us to go over is first, we're going to meet Tready. We'll provide a technical overview. One thing I'll mention is as you have questions, type them in the chat. We'll be monitoring those, and we'll answer them at the end, as well as probably some points in between if you guys have any questions. We welcome those as much as possible. After we finish that, I'm going to go over what I'll say is HEBI's approach, and it'll be the development of how we developed Tready, how we worked with a customer, a partner to do that, and how that kind of exemplifies the way we like to work as a company. The next section, kind of building on that, is actually a guest speaker. We're fortunate to have Dr. Alex Ramirez Serrano from the University of Calgary with us. He's a recent customer and somebody we partnered with in some really exciting robotics projects at his lab, and he's going to kind of give a great overview of his work as well. And then we're going to finish up with applications, kind of use cases that we see for Tready as a platform, some early proof of concepts that we've done, and where we think things can go moving forward. And kind of throughout this presentation, I'll probably keep mentioning the HEBI platform, development platform. We've actually done a webinar on that itself, and you can find that at hebirobotics.com/webinars, along with some other webinars we've done. So with that, let's meet Tready. So first of all, if I had to do a kind of a textbook definition for Tready, I would say it's a very versatile and agile mobility platform. What we introduced was definitely a robot with a set of specs and capabilities, but it really is kind of one example of a set of tools that we've put together that I think form a mobility platform. And it's focused on going outside in difficult terrain, climbing both natural and man-made obstacles like stairs. And as a company, we were also really interested in providing new robotic tools for confined spaces and constrained access in confined spaces. And we think Tready is kind of a good foundational starting point for that. At its core, it's a relatively simple platform rather than something more complex like a leg system. We have tracks, which is kind of a very traditional robotic platform, but we've added a degree of dexterity and flexibility by having those tracks articulate and building it around HEBI's modular actuators, which means that they're both powerful but also compliant, have the ability to control force. That's a theme that you'll hear through this presentation and really anytime we talk about the actuation side of HEBI's platform. Kind of main traits of the robot. First of all, it's quite powerful. So the actuators that we create focus on really high torque and slow speed. So it's a robot capable of putting out a lot of force, although it's generally slower than a typical high power system. So here's an example of the robot carrying 20 kilograms of payload over an obstacle that's a little bit more than a foot high. Another aspect is that it's dexterous, so it can move around in a very wide range of configurations. So climbing large obstacles as well as kind of getting itself out of flipped over situations. I'll show other examples later on of being able to use actually the flippers themselves to do some basic manipulation. And then dexterity extends to even things like arms and payloads and manipulators that you might put on top of the robot and coordinate with the base. And lastly, the robot is compliant. Even though it is very strong, the actuators that we use in the robot are what we call series elastic actuators. So there's actually a rubber spring in the actuator that allows us to control force and really acts as a shock absorber. So in addition to being strong, it's not strong but rigid like most traditional industrial robots. It has a level of compliance that I'll show that in the form of a manipulator with an arm lets us do kind of human-like motions for things like industrial inspection. But in the robot itself, it allows it to naturally comply to the terrain and obstacles without having to use really complex controllers, because the robot can passively comply to complex terrain. Going over some of the technical specifications of Tready, it's built around 8 R-series actuators. The R-series is our modular actuator that's sealed to IP67. So a big reason why the robot's able to be waterproof is that it all starts with the actuators. The building blocks themselves are already waterproof. To make everything wireless and self-sufficient, we have a sealed electrical box with an onboard computer and networking and Wi-Fi. It's powered with modular batteries that can be swapped out, but 4 of them give us roughly about 4 hours of runtime with this robot. And then the tracks are basically entirely, the track flippers are kind of entirely covered by tracks. We have custom 75mm wide molded rubber tracks. In terms of driving the robot, because it's built on our modular actuators, you have a choice of either high force actuators that are a little bit slower if you think you're going to be doing a lot of climbing and navigating obstacles, but you could also use a higher speed actuator if you're doing things like maybe doing pipe inspection, where it's going to be mostly flat and a higher speed throughputs more what you want. Because it's built on our platform, you can quickly integrate HEBI arm kits. This is an example of one of our standard R-series arms integrated on top, and you can coordinate both the arm and base seamlessly together. And we've been giving more and more thought to various payloads that you can put on. It's shown with a gripper here at the end of the arm, but before the end of the year, we're also going to have an integrated zoom camera with lighting. And I'll show we've also done some recent work with ultrasonic thickness probes. So the arm that you see here could be used for that. So the name of the game with this robot is to bring new capabilities into places that don't have it right now. Visual inspection is kind of the standard. Some systems do have methods for object retrieval, but being able to do things with a human-like level of dexterity, and then even do things that you would almost certainly need to send a human operator into a place for right now, for doing things like getting a spot thickness reading on a place where you've visually seen some damage when you're doing industrial inspection, are the kinds of things that we're looking to have this robot enable. Even more exciting for us is this robot, I think, should be thought of really as, like, again, the starting point for a platform that can be customized. So that big box that you see in the middle here, that's mostly to make the robot wireless, right? There's a computer, wireless networking, batteries. All of that goes away if you have a tethered system. And in that case, you could take these kind of track modules and put them together, fit into openings that are as small as about a foot circular diameter, and you'd still be able to mount an arm to it and have dexterous manipulation. The actuators themselves run Ethernet, so if you need to make a smaller, lighter, more compact system, we're already experimenting with configurations that look a lot like this. And so as we talk about Tready, and as you think about it, really think about it as kind of the starting point for a mobility platform, where there's going to be a lot of interesting things that can be customized coming out of this. So I can already tell you more configurations and accessories are in the works, and we really like to be customer driven. So working with customers to figure out what the next steps in the platform is really, we find to be the best way of working for everybody. And then lastly, the entire system is really made possible because of the software tools. The actuators and the hardware is what people see when we talk about the platform, but really just as important is the software tools, things like cross-platform software tools and APIs that let you develop with the environment you're most comfortable with. We have Android and iOS apps that allow quick prototyping for remote operation in terms of mapping functions to buttons and sliders to make a very flexible joystick that you can take out into the field. And then the APIs themselves cover a lot of that higher, middle and higher level of nuts and bolts that make a robot go. The joints themselves provide individual joint control, but we have a whole set of tools for kinematics, trajectories, all the things that it takes to coordinate kind of a complex set of systems, a complex set of joints, whether they're wheels, tracks, legs, arms. it's everything to kind of provide that motion control layer of your robot. And you can check out more at that at hebirobotics.com/APIs, as well as our documentation, docs.hebi.us. So with that, our next step is going to be going into kind of some background on how we developed the platform and HEBI's development process. But this would be a good time for us to take a few questions if there are any queued up already.
Yeah, we have a couple of questions here. One of them is kind of a straight up technical question. What is the size of Tready?
Yeah, so Tready is, and I'll say the data sheet is available on our website, but I've also got it in front of me here. With the tracks extended, Tready is about 1.1 meters long, so about 44 inches long. It's about 20 inches, about a ½ meter wide. It folds up into kind of a packed shape that's about 15 by 20 inches. And the robot weighs weighs about 25 kilograms, and then can carry another 20 kilogram payload on top of that.
Great, and one more. Could it be modified in the field, for example, equipped with a different type of arm or sensor?
Yeah, absolutely. That's usually one of the first things our customers do with any of our kits, is we kind of provide that base motion part, and then they put either our manipulator on top. I'll actually show an example of another customer that put a completely different tool on top. And then, yeah, other sensors are definitely a standard thing for people to integrate on. We break out both the battery power, some lower voltages for sensors, and Ethernet. The same thing that would send data up the tether is exposed to any sort of payload that sits on the top.
Great, and just a quick note is that size that you mentioned earlier is in the current configuration, though it is pretty highly customizable and smaller is possible.
Yeah, that's right. So if you're kind of thinking of it in terms of pieces parts, the flippers themselves are about 40 centimeters long, kind of about 16 inches long, and about 4 inches wide. But yeah, again, it's kind of the starting point for kind of pieces that you can rearrange however you like.
Great. Well, we will save any other questions for the end. Feel free to use that feature on the sidebar if you have any specific questions for us.
All right. So going into kind of how and why we developed Tready. HEBI as a company is one of the things I love about us is that we're really customer driven. And this whole kit project started with a customer that came to us and said that they were interested in our R series hexapod. They were interested in legged robots, ones that could travel outdoors. And a question that we like to ask, really early on in the process is, all right, that's awesome. So what's exactly the plan? How do you intend to use it? And what we find out is that this customer in particular is exploring really steep terrain and particularly inspecting areas that are prone to or maybe have already had landslides. And they had already been doing some work with legged robots and coming up with some limitations with those. And they were looking for other legged robots that could possibly do better. And so we said, yeah, okay, so that's interesting. Like, this thing's actually going out into the field. It's not just being used for research in the lab, and which is what most of the use cases for our legged platforms really do go toward researchers. But we really do think that our platform could provide kind of a practical robot that could go to the field and tackle the challenges and the terrains that you guys are looking to do today. So let's work together to iterate quickly and see if we can come up with something that really meets your needs. And we're able to do that really quickly because modularity is at our core. Kind of the base building part of it is the actuator. So the thing that actually provides motion, that actually moves to a position or provides a force. And we've, since 2016, been selling building blocks that do that with the X series. And for the last 3 years, we've also been selling kind of a sealed version of that same actuator called the R series. So whether it's indoors or outdoors, we have the building blocks to kind of get you started with robotic motion. And then what we like to do is we take those building blocks and the software tools and we iterate internally through several steps to do some development. And then at the end of this and most of our projects, we come out with a solution. But like I've shown kind of at the beginning, that solution is also new building blocks in the form of kits or kind of new subcomponents like these track bays that we can use to either start off other kits or build new projects. So it's a system, kind of a flywheel that feeds back into itself in a really great way. And so with this particular customer, we started off say, okay, we need to go up. Stairs actually wound up being a big part of this. So in addition to the natural part of slopes and landscapes, there's a lot of stair and kind of like ladder access up and down these things that the robot would have to be able to traverse. So in addition to looking at dirt and like vegetation covered slopes and rocks, we were looking at stairs. So we said, okay, what's the start simple, what's the simplest thing we can have to climb stairs? And of course, 2 tracks doesn't work very well. So we very quickly added a tail to it to stabilize itself, and we're able to get upstairs that way. And then from there, it very quickly grew into this kind of 2-track design that was kind of connected by a tail on either end. And that, after the first 2 weeks, led us into kind of doing some internal iteration on this kind of double joint design. So you can already see it's starting to look a lot like what the Tready system wound up being, but with kind of 2 articulated bodies as opposed to 4 articulated flippers. And we tested kind of different combination of actuators and torques and speeds and different kinds of payloads. And in this case, in addition to doing kind of steps, what you think of as steps, we're climbing something that's really more like a ladder. It's like a 60-degree ladder, because that was part of what the customer said. It needed to be able to fit into kind of a 1/2 meter width or a little bit more than that slot to be able to get up these stairs, and these stairs could be quite steep, like up to about 60 degrees. And then we took it to the field and added some other things that they were interested in terms of being able to provide visual inspection as well as manipulators to be able to move things, sample things. So we added this arm to the middle and kind of this pan tilt camera tail sticking up so that you could get kind of situational awareness while you were doing the manipulation. And then we took it out to the field and thrashed it around a little bit. And it's really important to push the limit of your system. Things don't always go according to plan. This is an example of we weren't controlling the track bodies quite as well, quite as compliantly as we could. The robot rolled backwards down some stairs, definitely took some damage to kind of the tail there. But because it's modular, within a few hours, we're able to just change out modules, get back to the field, change the software to have a little bit more compliance, change the controls that are available to the operator, and take it out and keep testing. And fortunately, Pittsburgh's also a really, really steep city, so there's no shortage of stairs and slopes to test out on. And then moving beyond, really, we're only getting started. So we iterated multiple times with that same set of hardware. A lot of the software kind of improved along with it. So with every system, we wind up kind of creating a new set of tools to control the robot in detail, kind of specific to not just the robot, but even the applications that the robots are going to be doing. And then we designed basically what is now Tready, based on both the lessons learned from the prototype and then also building it around the R series and building some new electronics enclosures so that it's fully sealed. And then really thinking about on this system, like the question earlier, providing affordances to integrate in particular other sensors, whether they're just visual sensors or LiDAR for 3D mapping and inspection, or even things like ultrasonic sensing for industrial inspection. So that's kind of the process of iterating through with a single customer. So for the next bit, I'm going to bring in one of our customers, Dr. Alex Ramirez Serrano, to provide an overview of his work.
Thank you, Dave. So
right.
it's a pleasure to be in this webinar. So as Dave said in his initial presentation, my name is Dr. Alex Ramirez Serrano. I'm a professor in mechanical engineering at the University of Calgary, where we have been developing robotics for a number of years. And maybe in the next slide, I'm going to tell you more or less what we're aiming to. So in my research group, we have been trying to develop robotics to penetrate confined spaces, work at high speeds, be fully autonomous, and all those things. So over the years, we have been developing navigation tools, control tools, sensing tools to enable these vehicles to go where no man has gone before, right? So the picture that you see there just basically just shows a little bit of snapshot on what are the things that we're trying to do with the leg robotics, ground vehicles, aerial robotics. Everything is targeted, or we're targeted to be able to fly in confined spaces as chaotic and confined and dangerous as what you will find in a collapsed building. For example, after an earthquake or tornado, if a structure collapses, usually you have to send search and rescue personnel, first responders, to try to find victims, assess the situation, and all those things. And those things are dangerous, put people at risk. So we have been trying to develop robotic systems to be able to remove people from harm's way and have tools that are not just only enhance their operations, but also provides the means for them to actually achieve their mission faster, more reliable, and with more confidence that everything will be okay at the end of the day. So if we can just switch to my next slide. So the type of operation, just for you to realize what we're trying to develop, in this slide just presents a quick snapshot of a disaster that happened some years ago in India, where you see there are people trying to climb on top of the rubble, trying to find victims. Sometimes they can access the openings. In many cases, they can access the openings. And as you can imagine, there's hazards when people and first responders try to achieve these missions. And it's not just a matter of trying to penetrate the space, but it's also trying to identify what potential hazards are present. You know, water, fumes, toxic gases, all those things. So we have been developing robots to be able to do that. And it's not just urban search and rescue, but also that this expands to industrial applications. And in the next slide, I just show a little bit about some examples of many industrial applications where we send humans and people to work in these confined spaces. And examples include the aerospace industry, oil and gas facilities, sewer systems, construction. There's a number of industries where there's a number of confined spaces that are, as you can imagine, just by seeing those pictures, it's not easy to work there. It's dangerous, and in many cases, people and workers will have to be equipped with safety devices, you know, masks, oxygen tanks, and all those things. So that even makes working in those conditions even more difficult. So one of the things that, as I mentioned before, our goal is to enable or provide to these people with tools that they can actually use to help them perform the work. In some cases, even just prevent them from going there and be able to perform the activities faster. So in that sense, we have been developing what we call a cricket. And the name is a little bit funny because our first goal was to develop a robot that was able to penetrate these spaces, reconfigure, change shape so that it can actually penetrate and overcome the many challenges that the robot will face. So based on the first designs that we started, I think like it was 5 years ago when we started designing this robot, the robot started looking like a cricket. Maybe what you see there on the pictures there, it doesn't look really like a cricket, but the first design iterations, it looked like a cricket, and so the name is stuck to the robot. So we call it the cricket. So the main characteristics of this robot is that uses legs, tracks, and with those things is able to walk, roll, climb. So that's what we call a hybrid robot, a system that can actually change its locomotion style based on the environment and also on its on what it senses from the space and its own motion characteristics. So what you see here in this slide, you just see a set of images that shows more or less what the robot can actually turn to be when you reconfigure the system. In the first slide in the middle, you just see the robot inside a pipeline where it was just inspecting corrosion in cracks that might take place inside the pipeline. Of course, it's difficult to penetrate these spaces. And then you can see that the robot can actually be reconfigured, which on what I call is a pancake type of flat configuration, where it can be used to penetrate really narrow spaces, potentially horizontal narrow spaces. But if it's a vertical narrow space, the robot can actually flip and then take a more narrow space in a vertical configuration. And of course, we have been developing techniques that enable the robot to climb ladders, as the picture that you see there on your left, and also being able to penetrate and move through vertical and horizontal pipelines. So this slide just shows you a snapshot of what we have been developing for about 5-6 years. But of course, we have different challenges. One of the challenges was, among many others, was, for example, we need the robot to be more powerful. The first design was powerful enough, but you know, as you start adding more sensors, deploying the robot in more aggressive conditions and so on, we started realizing that the robot needed more power. The joints needed to be compliant because we were penetrating and deploying the robot in situations that we didn't know what the robot will face. And of course, anybody in robotics might know that when you're sensing things, you might have errors. So by controlling the robot in a position type of controlled fashion, sometimes you're trying to step on something, but the environment is not what you think it is. So we wanted to add compliance. So, and then we started looking for how can we actually improve the capabilities of this robot to have compliance, be more powerful, be easy to control. At this stage, we were controlling everything through traditional systems like MATLAB and so on. And over the years, we have been switching more into using ROS, very powerful tool, user-friendly, and then we don't have to be reinventing the wheel. So at that time, unfortunately, we get to know HEBI Robotics, and they had the actuators that actually fit with what we were looking for. When we were thinking on modifying this vehicle, we were looking at making it more powerful by making it hydraulic, but it was too heavy. Maybe we have to carry equipment that we didn't need to carry and so on. But anyways, at the end we found HEBI, and the actuators actually fit many of the things that we were looking for, plus extra things, especially all the sensors that these actuators have. Is something that we needed in this robot. In this robot, we had encoders, and to be honest, you don't see here in the images, but we will break the encoders quite often. But anyway, so in the next slide, it's just I just show a picture of what HEBI actually helped us develop. Is in reality it's the same configuration, the same sort of kinematics and reconfiguration capabilities, and they were able to put it really quick, following our specifications. We were not here reinventing the wheel. Basically, we were just taking our previous design, try to make it more robust, faster, more powerful to be able to deploy in these conditions, especially because we are deploying these vehicles in real case scenarios, real situations, and we have been collaborating with search and rescue teams where we give them the robot and they tell us, you know what, they give us feedback. You know what, the robot works well here, but we have challenges here. The robot had troubles overcoming this obstacle, had troubles overcoming different features in the terrain. So with HEBI, we were able to do that really quick. So now we're in the process of developing the new generation of control techniques with the compliance characteristics that will actually will enable the robot to be more robust when people deploy these systems, especially because we're giving this robot to people that are not roboticists. So for them, it has to be a user-friendly tool that will be able to withstand the harsh conditions without having to know everything about how to program a robot, what are the sensors providing, and so on. And then here, there on the figure on the bottom, it just it shows there a little bit a human or robot or a human trying to traverse different terrains. So these are things that we are able to do with this robot. We can have it walk, eventually overcome large gaps in the terrain, then reconfigure to crawl, to go into tight spaces, climb, and so on. Of course, the robot is a big part, but of course, associated to that is the control aspects. And the robotics systems that HEBI has provided us with are facilitating these things in a tremendous way, especially once again because we don't have to worry too much about that the controller has to be that precise. The robot is able by default to be able to cope with those uncertainties and challenges that is facing every second that we deploy and use the robot. So anyways, that's a snapshot of what we have been developing. And I would just like to thank HEBI for enabling us to use their systems, which I think that will take us to the next step in our developments, in the sense that we're going to be able to now to use other more aggressive techniques in deploying these things. And hopefully at the end, the users will find this type of systems more user-friendly. I was talking to you about the previous robot that we developed. We tried to use it, develop it as user-friendly as possible. But of course, based on the fact that we're engineers and we didn't have the tools at that time to develop those things, we received many feedback, or a lot of feedback saying, what, we need this to be more user-friendly. And I think we're achieving those things with the new motors and with the new architecture that HEBI is providing us. And they're also going in the same direction of using rods, which is really important for us. So anyways, that's a little bit quick talk of what we have been doing. So thank you, HEBI. And I will pass the mic to you back, Dave.
Okay. Yeah, before I go on, I just want to give a chance if anybody has any questions for Dr. Ramirez Serrano. I'm sure we can accommodate a couple of those real quick. If not, I'll actually ask one real quick. So I do see drones all over your slides, and in terms of things like search and rescue, and we see it a lot as we learn more about industrial inspection, that seems to be like a trend where things are going. What other sorts of platforms and mobility are you looking at with your lab?
Well, we're that drone that you see in the picture there is the only aircraft that I know exists in the world that can hover, pitch, and roll. So basically, like a helicopter, you can hover like this horizontally, but with this drone, you can actually hover, pitch, and roll like this, and stay in the air in that position. So that allows us to penetrate confined spaces. But we're also looking to combine to deploy these vehicles, not just aerial vehicles, but ground vehicles, to be able to move from one environmental condition to another, such as from ground to water or from air to water. So we have been working on those things. So we have a lot of work to do, but that's the next step where we're going, to start merging these components in such a way that we, ideally, at the end of the day, we have a system that can reconfigure to any type of condition that it faces, and it can change its locomotion style to address whatever conditions are in front of the robot, and also be able to move between different environmental conditions. As I said, go underwater, go like perform like as a board on the surface, or even fly, right? And potentially, who knows, maybe even eventually go to space with the same system.
Awesome. Well, thank you very much for all of this.
Thank you, Dave.
All right. So to close out with, I'm going to go over a couple kind of applications and use cases where we think Tready's headed for, and kind of some of the 4 areas we've looked at are kind of indoor environments. You'll see actually kind of a lot of our overlap with our interests and the focuses of Dr. Ramirez Serrano. One thing I didn't mention at the beginning is HEBI Robotics came out of the Snake Robotics lab at Carnegie Mellon, and one of our biggest focuses in terms of applications was also urban search and rescue and industrial inspection. So that's something that's sort of baked into our DNA as well. So when people like Alex come along, like, we're super excited to work with them. So areas like indoor environments, construction, industrial inspection, which we've been doing kind of increasing amounts of work on beyond just Tready in the last 2 or 3 years, and then particularly confined space inspection. So kind of the first set of demonstrations I'll show are working, in, we'll say, indoor environments, right? But indoor environments may seem simple, but there's a lot of obstacles in terms of doors, stairs, thresholds, and then being able to, again, manipulate things and move things where you don't have an extreme amount of certainty. And so being able to customize and be compliant is kind of a key thing. So one example here I'll show, which I'll say that this is kind of working with a remote operator off to the side. So this is not like a fully autonomous sensed motion, but we have the ability and the force to be able to open a door, kind of compliantly open the handle. And this is an example of where you can use the flippers and the dexterity of Tready's base to perform some kind of basic assist to that motion. So using the flipper, we can actually pull the door open, while keeping the arm maybe available on the handle if we had to keep pulling if it had a closer, but really be able to do more than just move around. Similarly, here's an example of us moving a handle that's a little bit higher, and so you can also use the treads to get yourself a higher vantage point. Another example where if you want to take this to the extreme, you could kind of very quickly see you could modify the chassis to provide even kind of more of a lift depending upon how you arrange the flippers and the way they're attached to the chassis. Being compliant and having a lot of burst performance is important. So you'll see we were able to kind of sling the door open with a quick motion. So even though the actuators are relatively low power in kind of traditional robotic payload sense, right? We can only hold about 1 kilogram out at full reach, but we can provide these quick bursts of force within the power constraints of the actuator, so that kind of building on both the compliance, having hardware that's really smart, that's capable of peak performance, that's all things that's built into the system, so that you can really push the performance envelope of whatever system you see. And then one last thing I'll point out with this system is this is an example of mixing our X series and R series actuators. They're different form factors, but they all use the same protocols, the same software tools. It's really just that one is sealed and one is not. So when we're prototyping in-house, or if our customers are prototyping, it's really no problem mixing and matching those. Another example is working around in construction environments, places where we might want to particularly automate repetitive tasks or operate remotely. Anything where you want to be able to kind of provide a human look or a human reach into places that it might be dangerous to send people. The video here is an example of a project that we've worked together with some customers and partners in Europe, HD Lab, and a funding vehicle called TechMatch. So this is a customer that's putting together a tracked platform to get through construction sites and then remove paints and coatings from concrete wall. So in this case, we provided kind of the software tools and things that interface into this whole separate system that HD Lab provided, which is basically an abrasive sander with a suction system to take all the stuff off the surface of the concrete. So again, a repetitive task and an example of somebody very quickly integrating on a system where the kind of the arm part of it is something that they've supplied, but we provide the software tools to have it both be coordinated very easily and have the project come together very quickly. This project both kind of started and executed really over the course of a matter of weeks and a couple months to get from scratch to where the demo that you see here. The next section is industrial inspection and maintenance. We want to be able to both assist the automation of inspections, which we've been doing for the last couple of years in the case of fixed arms and smart robotic tools to help operators. And it's an example of where force control and modularity really enable this. So one of the big things we're looking at recently is the ultrasonic inspection, thickness inspection of complicated geometries. So there are robotic systems that inspect flat plates, flat pipes with UT probes that need to measure the thickness, but these probes basically need to be coupled to a surface where they're held across the surface kind of in a normal angle and held in contact. And so for systems where for places where the surfaces get complicated, like elbows, T's, reducers, which also happens to be where a lot of the problems are when doing industrial inspection, HEBI's tools wind up being a really good starting point for prototyping how, and actually solving in the field how to do this, because we can handle both the complex motions, complex geometries, because we can coordinate so many degrees of freedom, but also we can be inherently compliant. We can go not just to a point in space, but we can, while we're at that point, push in with a certain amount of force and be compliant and really reliably inspect surfaces, even though we may not know with sub-millimeter precision what that surface looks like. So that's an example of us doing ultrasonic inspection with a fixed arm. And we're also looking at things like cleaning and maintenance. So this is an example of putting a similar arm with a sprayer for things like covering a surface, removing coatings. There's a lot of places where you're either the media that you're blasting with itself is fairly dangerous, or the coatings you're trying to take off are dangerous. So being able to provide coverage that would normally have to happen with a human operator in place, there's some real advantages to being able to automate that and bring that to a remote environment. So those are the sorts of things we're looking at there. And then lastly, confined space inspection, being able to do all of this and either fit in through a small access and then unfold into a larger area, or maybe even just do things like inspection of extremely challenging, maybe sewer and wastewater pipes. Big thing to highlight here is all of the things about Tready and the R series system are designed to IP67, so they can be submersed for 30 minutes under at least a meter of water. And it's very quick to add arms, sensors, different things for a variety of tasks. And this is one where the tethered operation is really important. In most of these situations, the robot's going to be tethered, and that's what gives us an opportunity to really shrink it down potentially in the future from what you see here. So to test this out, we took it to the house of our Chief Operating Officer, Bob Rada, and we put it down in some of the storm drains. So this is an example of, we got down into just put the robot down in the catch basin, and this is an example of using the flippers to get up a gap so that you wouldn't actually have to necessarily send a person down into the basin to get the robot inserted. You can do that remotely. And then once it gets in, we can just flip the tracks around, drive, start inspecting. Once you're in the pipe, this one's a bit of a straight shot, but talking to customers or talking to people that we know that do sewer inspection for a living, storm sewers in particular can be extremely challenging in the sense that anything that's on the street can wash down in there, whether it's sticks, trees, railroad ties, engine blocks. Apparently you wouldn't be able to imagine all the things that's in a storm sewer that you might actually have to overcome and crawl over to get that last maybe 10% of an inspection that's still really important to the city, but requires some specialized equipment to be able to get through it. And so to wrap up, just kind of finishing with what I hope you guys were able to take away today. Tready, in addition to being the newest addition to HEBI's mobile robot kits, it's built on a platform and really is a platform that can be extended for other solutions. I demonstrated a little bit about the process that HEBI likes to use to be customer driven, create really practical solutions to people's problems with robotic tools, and really how that feeds back into itself to accelerate the future of robotics, right? Everything we do kind of comes back into the platform, helps those same customers, future customers, and just keeps going. I would love if you could learn more. If you want to learn more, welcome you to visit hebirobotics.com or our technical documentation at docs.hebi.us. Like I said, the video that I played at the beginning of this presentation and lots of others are at our YouTube channel as well. And with that, I'd like to thank everybody for taking the time and attending today. In particular, I'd like to thank two other people at HEBI. Andrew Willig, our senior mechanical engineer, he really did most of the legwork that you see in front of you in terms of the hardware design and all the work on Tready. Willig's done some fantastic work there. And really most of the work in setting up this webinar and getting things coordinated goes to Kamal Carter, our sales engineer. So he's a relatively new addition to the team, but having him has been and continues to be absolutely fantastic. So thank you. With that, that wraps it up for me. I'm happy to take any questions that people might have while we still have some time.
Yeah, I have a couple of really excellent questions here. First one is there any intelligence in Tready?
Depending upon who's asking the question, the answer is either like yes or no. For me, as a mechanical engineer, I'd say there's tons of intelligence baked into Tready in terms of the actuators have the ability to control force, so there's a lot of calibration, a lot of sensing in the actuators. There are safety controllers at multiple layers to the robots that let you kind of in the field exploit the performance, but making sure that the actuators themselves don't break. Like you heard Dr. Ramirez Serrano mention that the encoders on his robot broke. Like unreliability is a big thing that holds robotics back. Like these are complex systems that do break often. So we've employed a lot of really software intelligence in the module to make them extremely reliable, in addition to a robust mechanical design. In terms of, if you're thinking intelligence at a higher level, in terms of like navigation planning, that's sort of like the one layer above what HEBI provides. So we do not have systems that are necessarily like fully autonomous out of the box. Kind of the first things that most of our customers do is they add sensors, add perception, add additional computing to handle all of that. But what we try to do is make the physical part of the robot, make that higher level intelligence part go as smoothly as possible.
Excellent, thank you. And kind of a two-part question. First of all, what is the distance that Tready can go tethered versus untethered?
Yeah, so tethered, kind of, I'll say out of the box right now, our limit is about 100 meters, because that's what you can do to push Ethernet over a tether. Now that said, there's with relatively off-the-shelf development, it's development, but including off-the-shelf parts, you can run things like a fiber optic tether that can go miles, right, on a very lightweight tether. In terms of wireless, well, we have found out that wireless does not work underwater. We had Tready spend more time than we had cared to under a river, and although it was still good after that, by finding out that Wi-Fi doesn't work underwater. But if with directional antennas, you can run Wi-Fi over certainly hundreds of meters, depending upon what you're doing. The main thing about that is, it's one of the main reasons why we built everything around Ethernet, because there are off-the-shelf tools that kind of, regardless of what your requirements are in terms of wired versus wireless, there's a lot of off-the-shelf options that you can use for whatever the situation matches.
Great, and similar to that, does the operator have to be in line of sight?
No, not necessarily. If you have a camera on it, we have all the ability to send that camera feed either over a tether or wireless. So even though like most things that HEBI provides to a customer out of the box would be like a remotely controlled demo, we will have all the tools put in place so that it could be tele-operated as opposed to remote control. So basically working over a video feed as opposed to actually being able to see it third person.
Excellent, and I just have a couple more here. First one is, are you working with any other companies or partners to develop application-specific Treadys, and are you looking for partners?
The short answer is yes and yes. We're always looking for partners. Like I said, once I kind of put together the concept with the sort of version of Tready that you see on the right, you can't sort of unsee it. So there's things that we're playing around both in-house and with others. And yeah, we're always looking for more customers, and really we just love having phone calls and meetings with people that have problems, even if they don't have a specific thing in mind. People will say, hey, here's a challenging task that I have that happens to be in a confined space. Do you mind if we just get on the phone for a half hour and I tell you about it? And we love learning about things like that and getting to the field and finding out what the challenges are as much as possible.
Excellent, and then I just have two more for you, Dave. One is it all silent?
No, the robot sadly is not silent. The actuators have spur gears. They're not like loud near earplugs or anything. But I'd say if you have some sort of military application in mind where it has to be like super silent, this system as it sits right now is not ready for that. But we're always looking to understand what the requirements for actuation are in general. We have talked to other people for which noise is the thing, but these actuators are, I will say, not silent.
Gotcha. And the last question here is, what is the most interesting sensor payload you've tried? Are there any limits to what sensors you could put on this?
I'd say to go backwards, I'd say the two limits to sensor payloads are kind of a practical one of weight, right? So if it needs to just sit on top of the box, it can be pretty heavy, right? It could weigh 20, 30 pounds if it's just going to sit on the chassis. If it needs to be at the end of the arm, I'd say there's a practical limit of maybe 1 kilogram, 2 or 3 pounds. if you expect to be able to reach it up, move it around, again, with the tools that we have today. We are working on larger actuators. Some of the most interesting ones I think recently are things related to thickness inspection, both ultrasonic, also things that don't require water coupling to measure thickness. So there's a lot of interesting new technology in that area in terms of kind of simple pen-like probes that the thickness reading itself coupled with even a little bit of motion data, right? So there's kind of a line where you can walk where you can put a very fancy sensor on the end and put it in a spot and get some data, or maybe you could take a simpler sensor, move it around, and if you can measure things about that data, you can do some very powerful stuff there. So I think some of the most interesting ones, at least from our perspective, are kind of established boring thickness sensors, but starting to be able to do some very interesting things by coupling it with all the motion data and all the other kind of robotic data that you get from the system while using it.
Excellent. So that's what we've got question-wise. Do you have anything else, Dave?
No, that's all I've got. Yeah, thank you everybody for your time, and hopefully we'll see you at the next webinar.
Yeah, and if you have any questions or if you would like a quote, feel free to email us at info@HEBI Robotics. We'll get back to you.
All right, thanks.